Assalamu alaikum. In this lab, we are going to implement a binary search tree as a linked list of nodes. So this lab will basically give the concept of binary search trees, how to insert into binary search trees, how to search data in binary search trees, and later on in the next session, we would see how to traverse a binary search tree. So as we have discussed in the class, a binary search tree is basically a tree data structure that is binary in nature, which means that it can have every node can have maximum two children. And what makes it a binary search tree is basically the limitation that or the constraint that every node will have the values less than itself as its left subtree or its left child, and the value greater than this node value would exist in its right subtree. So if this condition is met in all of these nodes, then it is a binary search tree. So the basic operations that we perform on binary search tree are searching data, and traversing of this binary search tree. So for insertion, the algorithm is pretty straightforward. That first of all, you check the root. If the root is null, it means the binary search tree is empty. We would call binary search tree as BST from now on. So if the root is null, then BST is empty, so you just create a new node and you make root point to this new node. If the root already exists, then it means that the tree is not empty. So now you have to find out the actual the position where you would be inserting this new node. For example, if there is a root node which has a value of 50 and you are inserting 30, so you will compare this data with the root node or with any node in that matter. So if the data is less, then you have to go to the left subtree or the left child. And so on. Again, for for the left child, you will compare the data with the data of this left child. If the data is less, then you will go to the left child of this left child itself. So you keep on going to left child if the data is less than the node's value. And so when this node when you come across a null, so that is the required location where you want to insert the data. If the data is greater than the node value, then you go to right. Okay, so we would be implementing this algorithm. For searching, it's as simple as insertion, that you the value you are going to search, you compare the root node. If it's null, then it means that the value of the tree is the BST is empty, so there's no value exists in this tree. If the root is not empty, then which is indicated by root not equal to null, then you start looking for the value. So you compare the root node's value with your key that you are going to search. If the key is less than the root node value, then you move towards the left. If the key is greater, then you move towards the right, and you do keep doing on this comparison for every node until you either reach your required node, which is the key value that you are searching, or you encounter a null. In both cases, you return that node. If it's null, then you return null. If it's some node, then you return that node. So now we would be seeing an implementation of this algorithm for searching and insertion, and later on we would be manipulating, you would be changing a little bit in this implementation to make it run for this class data item, which you have also manipulated in priority queues lab. So in the same way, you would change this code so that it inserts these data item objects into the binary search tree, and the comparison is made according to the length of the string of this data item object. And here is the condition that the string in the object of item with minimum characters has the greatest value. So for example, if you insert D1, which is which has the string Farhan. So because the BST is empty, so it would become the root node. Then you insert another value DSA. Since it has less characters than Farhan, so it has greater value, so it comes to the right. Then there is this string data structure and analysis. It has a greater number of characters, so it has less value than Farhan, so it comes to the left, and so on and so forth. So let's move towards the implementation. We would be implementing this in a new files from scratch so that you have an idea of how things work. Let's call it a BST class, binary search tree. First of all, for this BST class, we need uh, we need to make a node class. So we can either create another class for that, or we can just create it inside this BST class. Let's call it a node class. And okay, so this node class has basically let's suppose an integer variable for data, and then it has a left child which is of the same type node. Let's call it left and right. Uh, it has two pointers to the left and right nodes of a node, or left or right children of a node. Okay, so now we need a few constructors for this. So instead of constructor, let's suppose we have a utility method, which is a static method, and and it returns a node to us. Let's call it new node method. Okay, it creates a new node and returns to us for every value that we pass it. Okay, let's suppose call it key, and what it does is it returns to us a new node by creating a new node. Let's suppose a new node is equal to new node. Okay, and what it does is it sets the new node's data to the key that we pass it, and it also initializes the left and right subchildren of this new node that we just created to null. Okay, so this method would return us this the pointer to this new node. Okay, so now we implement the actual methods of this BST class, the binary search tree class, the insert method. Okay, so insert, it returns a node, it returns a pointer to the node that we will insert. Okay, and let's pass it a key value. Okay, so first of all we create a new node by by calling this new node method. So we say node, let's suppose new node is equal to, we call the method and pass it this value key. Okay, so now we have to insert our this new node that we just created into our BST. For that we first check the root. So we see that if root is equal to we compare it against, so if this root is equal to null, if root is equal to, okay, we have to pass the root here as well, because every time we want to insert a a node into the BST, we pass the root node of this BST, so that starting from root, the suitable location for this new node is searched. So we check that if root is equal to null, then we just what we do is we just point it means that the BST is empty, so the root node can be this new node. And we point the root this new node with root, and we return root. Okay, otherwise if root is not equal to null, then what we do is we start looking for the suitable location for this new node. For this, first of all, we create a temporary node. We call it a temporary pointer to a node. We call it current, and another node we call it parent. Okay, we have discussed this in the class, why we need these current and parent pointers. Then we initialize this current to the root. Now inside a loop, this loop can be always true, because we return inside this loop whenever a suitable location is found and the root is and the node is inserted. We just return from this loop. So therefore we don't need to necessarily compare any condition for this while loop to be true. So first of all, what we do is we initialize the parent with the current. Then we compare the current value. We compare the current data. If this current dot data is less than if this the key that we are going to insert, or the data value of the node that we are going to insert, we can compare it with key, or else we can compare it with new node dot data, because here we have this new node and it has the key value. So if key is less than current dot data, then we have to go to the left subtree of this current or the root. Okay, in that case, what we do is we move the current pointer to current is equal to current dot left child, or current dot left. Okay, and we also compare in this case, if this can be the case that the current is pointing to a leaf node which does not have any further left child. So if and when we move the current to the left, then it means that we have made current equal to null. So in that case, we compare that if current is equal to null, then what we do is we make the parent, which was equal to current, inside the while loop we made parent equal to current. So, and we made parent equal to current for this thing, that when the required location is reached, then we have the pointer to the parent of that node. So because parent dot left is equal to new node, will insert this node, and then we return the parent dot left. This returning is optional. You can remove this return type node, and it would not ask you for returning a pointer. Okay, so if this is the case, if this key is less than current dot data, then we do all that. Okay, and then in else, what we do is because if the current key is not less than current dot data, then it must be greater than current dot data. In that case, we move the current pointer to the right subtree of this current pointer. So we move it to right, and again we check that if this current has been equal to null, if current is equal to null, then what we do is we point our new node, insert our new node, parent dot right points to the new node. Okay, and we return parent dot write in this way. So yeah, this is basically the insert method, and we have to end the while loop. Okay, so this statement, this closing bracket here is ending the while loop, and then the insert method also ends here. Yeah, this is the insert and this is the end class. Okay, before moving towards the testing of this method, we also define the search method. So what the search method does is basically it returns a node, uh, and we pass it the root of a BST and a value to be searched. Okay, and then what it does is basically it first of all checks that if root is equal to null, then we return root or return null, whatever, because they are they have the same value. Else, or if you don't put it in else, it's fine. What we do is basically the same. We in this case we won't need a parent because we just have to return the current. So what we do is in while loop, uh, first of all we initialize the current node with root, and while true, okay, okay, so we basically compare here, not, we don't always run this while loop as a true. We compare while current, while key that we are going to look for, while key is less than current dot data, then while key is not equal to current dot data, because we are going to look for this key. While key is not equal to current dot data, in that case what we do is if if it's not equal to current dot data, then it must either be less than data. So if key is less than current dot data, then current is equal to current dot left. Else current is equal to current dot right. Okay, and then we check if current is equal to null. So return current. Okay, and otherwise also return current. So it means that the key has not been found, and eventually this current has become null, so we would return this null. Okay, so this is the search method. Now we implement the main function for this, for testing these methods. Okay, we just add a few more statements to clarify the result of the search. For example, if current is equal to null, if current becomes null, then we print a message that value not found. Okay, or node not found, whatever. And in case if this while loop condition is false, it means that this key has become equal to some current dot data. So in that case, it means that the value has been found, or node found. Okay, so this will just clarify the search result. Uh, so now we include the main. Let me just pause this recording. And okay, before running the main, I would just like to indicate that these methods should be made static, because we have static context in the class. Also this method, okay, so let's first not include this traversal method here. So what we do, we want to create this kind of structure for a tree: 50, 30, 70, 20, 40, 60, 80, and we initialize the root node to null, and then we inserted 50, and then we insert 30 and 20 and 40 and 70, 60, 80, etc. So since we are not in this lab session, we are not going to discuss the traversal method. So if this uh, if this insertion, all these insertions don't return a null, so it means that the values have been inserted successfully, and we compare it with, let's suppose, calling the search method, and we pass it some value. Let's suppose we pass it the root, and we pass it so we pass it 40, and then for example we pass it another value, 80. Okay, and then we pass it another value 100. Let's see what if the code is running properly. Okay, and then we run node found, and value not found. So in this way we know that these values have been inserted into the BST, and the search method is also working properly. So I would recommend you to implement this with yourself, get it implemented, and then run it, and come across different problems if there are any, so that we can discuss them in the lab session. And one other thing that I would recommend you is to implement this insertion and searching methods recursively. Okay, so we have discussed that in class, that instead of comparing and looping across all the nodes in BST, you can use the recursive method, which makes the implementation code a lot simpler and a lot shorter, and it involves recursion and pushing the addresses to the stack, and popping from the stack and returning to the addresses. It is basically implementation becomes simpler. The processing is not our headache. It's of course compilers, so we are not concerned with what compiler does to return the methods, to pop the addresses and pop the variables and return to the calling points. It's all done by compilers. So I would recommend to implement both insert and search methods recursively. Thank you very much.